and also in preventive medicine and population health. Dr. Gray received his medical degree from the University of Alabama at Birmingham School of Medicine and his master's in public health degree from Johns Hopkins School of Hygiene and Public Health. He did his residency at Walter Reed Army Institute of Research in Washington. In his research program, Dr. Gray has conducted diverse epidemiological studies of infectious diseases all over the world. Much of his work has involved identifying risk factors for occupational diseases, particularly for respiratory virus infections. He has studied numerous occupational groups, including military personnel, farmers, animal breeders, veterinarians, and other types of animal workers. As you'll hear, Dr. Gray is a very strong supporter for the One Health approach that I'm sure most of you have heard about. And he's won multiple One Health research and training grants. He's helped establish centers for One Health in not only the US, but also in Romania and China. And he's also developed a number of graduate programs in One Health. Finally, Dr. Gray is a fellow in the Infectious Diseases Society and a member of the Council on Foreign Relations. And so welcome, Dr. Gray. The title of his talk is Mitigating Future Pandemics, New Threats and Strategies to Consider.
Well, thank you very much, Terry. Those were very kind words, and it's a pleasure to be here. It's an honor and a special one in that I see at least two of you are from UTMB, which I've recently joined, and I'm so glad to be here. So what I'm going to try to do today is look into the future a bit and think about what we could do a bit better than we've done before with respect to pandemics. First, we just need to review. We're almost numb to these statistics now, but 337 million cases and over 5 million deaths across the world. It's just unacceptable. We have to do something more. And of course, these counts are continuing and much of it is now below the radar. We're not even going to be able to count the morbidity and mortality. Well, I think Julie Gerberding said it well in this testimony she did in 2019, just before the pandemic. When biothreats are recognized, policymakers do allocate resources, emergency resources, but once the crisis fades and public attention subsides, investments dry up and attention shifts and a false sense of security takes hold. And I liken this to the whack-a-mole pandemic response strategy. You know, we sort of wait for something to happen and then we try to slam it down. But it's tremendously costly. Isn't there something we could do better? And, you know, to anticipate these things without breaking the bank. Well, I think along those ends, we need to think about, you know, how these particularly zoonotic pathogens are spilling over from animals. And of course, we know that they can come from all sorts of different animals, and they can come through various different modes of transmission. But I think what is often not recognized is that it takes a lot of time for viruses that are circulating, for instance, in large dense populations of animals to challenge our immune systems and take a foothold. Many of these exposures cause no infection. Very few that do cause infection are limited. It may or may not cause disease. And a very small subset of these may see some limited human-to-human transmission, and even rarer still would be, you know, very efficient transmission. And I like to think of this from an evolutionary perspective, that, you know, to be successful both in the animal host and be able to subvert our immune system, that takes a lot of chance and takes a long time. So if we're able to detect these viruses as they're beginning to spill over, beginning to have success, then it would be a better way, you know, to implement strategies and detections rather than waiting for them to be highly efficient. Well, we have time. The evolutionary clock ticks slowly for the most part. And this is an earlier paper looking at the phylogenetic parenthood, if you will, of the early SARS-CoV-2 viruses. And I show it to illustrate the point that these viruses, at least from which SARS-CoV-2 are thought to have circulated, a number of years back. And so if there was a way to detect them before they fully became efficient, well, we could develop diagnostics and hopefully interventions. Well, how could we do that? How could we efficiently conduct surveillance and do so at a sustainable cost? One of the reasons that we have the whack-a-mole strategy is it's expensive and people don't see immediate results. They cancel the programs. Well, there have been a number of different measures to attempt to do this. One of the most popular or famous, if you will, in the United States is the USAID's Predict 1 and 2 programs. And in those programs, we have invested in excess of 200 million since 2009, collected 140,000 biological samples, identified, they say, some 1,200 novel viruses. But the approach has been criticized. It's been adjusted over time. But it's been criticized as, well, what does it mean when you find a novel virus in a bat or a reptile? Is that really a threat to humans? Will it ever be a threat to humans? And so there's been some refinement of this strategy and a new approach we'll talk about in a minute. Another approach is to say, well, we don't know what's going to next threaten us, so let's intensively study the families of threats that are recognized. Let's develop viral constructs that we can pull off the shelf. Maybe they've been through phase 1 safety trials, immunogenicity trials, and let's get those ready. We'll save some time and we can adjust them antigenically. And that's had some success, and we've done that especially for influenza, but also recently through these Centers for Excellence in Emerging Infectious Diseases, of which we have 2 at UTMB. So they have basically 2 poles of intervention, if you will. One is to focus on wildlife and pathogen discovery, look for strange viruses out there, and they're in addition to the USAID, there's a new program, the old Predict 1 and 2, new program called Deep VZN, of which I'm proud to be a part, where we're attempting to look at high-risk geographical areas and countries where we think there's likely emergence for threats. But again, it has a wild animal heavy focus. There's also something called the Global Virome Project, which is incredibly ambitious, to look for viruses in most of the animals in the world and genetically understand their construct. The other part of this pendulum pole is the human constructs. Let's look at human pathogens. Let's study their pathology, immunology, and develop vaccines. And as I showed here, we've got NIH investing in those and a number of similar institutions in the UK and of course the CDC. But what I'm going to try to argue is that these have been all criticized, both these ways. And what we need is something in between. We need to find out in an efficient way what is already spilling over in novel. What is the likely to impact large populations because we have very little immune protection against viruses. Now, I'm not alone. Other people are saying, we really need to focus on the human-animal interface if we want to accurately get a handle on zoonotic risk. And that's pretty remarkable because many of the modelers have also, because the available data has a heavily imputation of wildlife, it focused on wildlife. Well, if you wanted to look for pathogens, there are.
Yeah, I need her to resend me Crystal's Uh,
If you want to look at pathogens, there are certainly many pathogens that are threats to our health, and perhaps fewer pathogens that are pandemic threats. We can think of Yersinia pestis, of course, and antimicrobial resistance, and arboviruses, and enteric pathogens. But it's the respiratory pathogens that, at least time and time again, have caused us the most trouble, because often, as we've seen with SARS-CoV-2, a lot of the movement is subclinical. And for some of these, up until recently, we really didn't have any good pharmaceutical or immunological interventions. So really hard, they move fast, they spread fast, and they spread subclinically. And so very difficult to stop. Well, if you think about those as sort of at least an important focus of your surveillance systems, we can look at where the human-animal interface has yielded spillover in humans. And here we've attempted to do this in this paper in Frontiers of Public Health, and graphically show not only the sort of relative size of these epidemics, but also some of the animal reservoirs involved, at least for those that are zoonotic. And we've attempted in this other paper to quantify this even more, and in doing so, narrowed it down to 5 viral families. So when you think about investing in surveillance, it really helps if you can do a data reduction with respect to targeted surveillance, and you don't have to spend as much looking for everything that's a possible threat. So if you were to focus on these 5 viral families, we think that you would pick up most of the threats. And we know a lot about at least the influenza family of viruses. And we can think about, well, if you're anticipating a spillover event from animals, which animals have the highest probability of causing a spillover event? And you can look at these data and you can say, well, for influenza A, it seems that the swine-human interface has a higher probability of spillover events than, say, the canine human interface or the equine human interface. So you can do some prioritizing, if you will, for these families of viruses. Other colleagues have looked at the coronaviridae and said, again, well, where do we expect to see high probability of spillover event? And you can see here, pigs again are the #1 candidate. And it's easy to see because they've had a lot of unique emerging viruses. Fortunately, these that are shown on the right column have not spilled over to humans, but they're definitely, these large pig facilities are definitely novel virus generators. A lot of that has to do with the tolerance for the pigs. It doesn't kill the pigs, many of the novel viruses. They have a long growth period, 6 months versus poultry, which is much shorter. So viruses have a tendency to get into these populations and churn, replicate, mutate, recombine, and you see the results here. It makes sense that these are a threat, both mathematically and observationally. Of course, there are other animal hosts that we need to be aware of, but the point is you can quantify this risk and use that to set up your surveillance. So we benefited a lot by talking with veterinarians and asking them, well, how would you look for a novel coronavirus in your animal populations? What sort of diagnostics would you use? And it turns out that there are a lot of pan-species diagnostics, as well as very sensitive and specific targeted diagnostics. And with the idea of bringing these capabilities for novel virus detection to the developing world, we developed algorithms that combine both real-time assessments and regular PCR, RT-PCR, conventional PCR assessments, and partnered with our colleagues in the developing world and looking for these viruses, often at the human-animal interface. We've done that not just for the influenza viruses and the coronaviruses, but also the adenoviruses, the enteroviruses, and the paramyxoviruses, and have been funded by federal government actually to do workshops and such. We've actually sort of capsulated this all in this viruses paper published just last year. It has a supplement with totaling 39 pages with detailed SOPs on how to do this. And, it bears, it's something that people can copy and bring up in their laboratories in the developing world. And so our partners, often veterinarians in the developing world, have benefited from support from the U.S. government in transferring these technologies and bringing them up. And of course, now what is being done is looking at next generation non-biased pathogen detection to sort of supplement this. Of course, you can't do that on every specimen. It's much less costly to use conventional real-time assays. We've done this now with two different strategies. The best strategy, as I've tried to portray here, is to look at the animal worker animal interface. Think about where you have dense populations of animals in close proximity with intense exposure to the humans. That could be live animal markets, that could be big confined animal feeding operations, that could be meat processing centers, at least where they first would encounter a live host, and do surveillance there. See what viruses are in the animals and look in as best you can through non-invasive ways, such as nasal washes, aerial sampling, water sampling, for evidence that those viruses are in the environment and threatening, if not infecting, the animal workers. And then from your analysis of these, determine which of those viruses you want to invest more in developing diagnostics and interventions. If you can't do the human-animal interface, which I'll tell you, in the United States, that's very tough to do because we have a very powerful animal meat industry, and they don't want us in there because it threatens, if we were to find something, it could threaten their businesses. An alternative strategy would be to do pneumonia etiology surveillance in geographical areas of high risk. And so that's our fallback position when we can't get the cooperation to study large populations of animals. Now, this is a concept that many of you have heard of, the idea of working across disciplines, human health and animal health. And a third dimension of this is environmental health. And under this interdisciplinary concept is called One Health. And so this is being bantered around. It's being embraced by all sorts of senior policy makers here in the United States as well as abroad. And it seems to be a way to tackle very challenging, complex interdisciplinary problems by bringing stakeholders to the table and designing surveillance. And so if you haven't jumped onto this bandwagon, it might be strategic to do so because there's funding. There's funding now, and there's funding that seems to be projected in the future. Well, where might you look for spillover events, at least associated with dense populations of animals? This is a graphic depiction of some available data associated with livestock zoonoses that was captured and graphically depicted here by the PREDICT program. And you can see that we have a lot of these threats in dense populated areas, and there's a lot of interest in Africa and especially in Asia. And so I'll just tell you that Asia has been the focus of Deep VZN and will be the focus of other products, expert teams thinking about what to do in this that are being convened even now at the national level. Well, we had the opportunity when I was at Duke until just a few months ago of setting up studies, some funded by the NIH, some funded internally some by the DoD, in a number of countries where we attempted to do One Health-oriented studies at the human-animal interface. And at this time, I had a laboratory in China and also in Singapore. So we were able to bring the specimens into these laboratories and work them up when we couldn't finish the work in the country of origin. And I'll just say it's a lot of fun. You know, the veterinarians, I think some of you are from veterinary schools. For me, on the human side, I had no idea of the richness and of knowledge and the difference in perspective, how naturally, like in human public health, you look at populations and you know, you look at the world differently, but you don't often have the deep pockets of funding and the capabilities. So it's been enlightening. It's been a lot of fun to try to bring new technologies to our partners in the developing world and send them out to, you know, think about where they think the spillover events were likely to occur in their country and help them develop the surveillance studies. And they in turn have brought us to some pretty exotic areas. And we've seen, you know, how they best attempt to mitigate it. I don't know about you, but and I don't know if it works, but in Eastern Malaysia, in their live bird markets, they wrap the birds in newspaper to reduce fecal exposure to the public and to the workers from enzootic avian influenza. I mean, it's low tech and maybe it works, who knows? But it's interesting to see how different cultures recognize the problem and attempt to mitigate it. And we're of course seeing changes now quite a bit in China with respect to the live animal markets, which up until just a few years ago, the number of animals, especially in Guangdong province, the diversity was just astounding. Now we're fortunate to have some funding. This is a study we just wrapped up in China with partners in the military. Can you believe that? And also folks from the provincial and the large city CDCs who did much of the field work for free and laboratory work for free. But in this prospective study, we followed 300 pig workers and 100 non-exposed workers. And it turned out after about 4 years of work that they had a very dynamic farming. And so we had like 12 farms involved, not the 6 that are shown here. We would sample the workers with nasal washes every month and annual serum sampling questionnaires monthly. And we looked for influenza-like illness. We also sampled their pigs with rope sampling, which is, you know, to grab a pig and get a nasal sample is really tough. Some people do nasal wipes, but to get a deep sample with a 300-pound pig is pretty impossible unless you snare them, and that means grabbing them by the mouth and hurting them. And so using non-invasive techniques like aerosol sampling, rope hang sampling, and fecal sampling are a way to get the cooperation of the industry without, you know, threatening their livelihood. And finally, we also, as I mentioned, worked on the farms, doing not only fecal and aerosol, but also water samples and environmental swabs. And it's a huge complex study we could never do here in the United States because it's so costly to do, you know, have so many people involved and have all these specimens detected and attempts at isolation and sequencing, et cetera. But in China, I'll just say that up until recently, we have wonderful cooperation and they provided the manpower to make it successful. And the work basically reinforced what had been hypothesized years ago, and that is that it's really true that the human-pig interface is a high-risk interface for human infection, whatever is enzootic in the pigs. And there's a whole bunch of mixing going on, mixing from passerine birds, from dogs and cats that cohabitate, from ducks and geese and chickens that are right next to the open no windowed pig barn. And so the probability of mixing of influenza viruses and other viruses that are endemic and zootic is very real. And we have the data here to demonstrate that with a fourth paper and now under review. So it's possible to do these studies, but you have to have really good cooperation. Another place where we've had good cooperation is the Asian country of Mongolia. We're now talking about what's sometimes called Outer Mongolia, not the semi-autonomous province Inner Mongolia, which is in China. This is one of the coldest, Ulaanbaatar, the coldest capital in the world, is home to really hardy people who live very much in close proximity to animals. So we were able, as funded by the Fogarty International Center, to partner Americans, one American with 2 Mongolian young scholars, and do One Health-oriented studies focused on 4 different zoonotic problems in Mongolia: tick-borne disease, influenza, parasitic disease, mosquito-borne diseases, and basically train these young folks. Ideally, we had human health, environmental health, and veterinary health on each of the teams. We trained them for about 3 months in the United States. We said, pick a problem, design an approach, and we'll give you a certain amount of money to do it, and go do it. So this was a pretty darn successful program for me. I learned a lot. I think we've had in excess of 25 publications from this. And a lot of our trainees went on to research careers. A number are now young faculty members in the US, particularly on the American side. So this One Health approach can be taught if you can get permission to do it. And we were able to do that in Mongolia. Now, where we couldn't do One Health, we sometimes would do the pneumonia approach. We say, well, we know your geographical area is high risk for emerging pathogens based on population and previous data, population size and previous data. Can you do a pneumonia etiology study? That is, people that are sick enough to be hospitalized, all we want is a nasal swab and some questionnaires, and we'll employ our pan-species and routine diagnostics and look for novel agents. And it turns out, because we were giving new diagnostic capability to some of these folks, and we were giving them the reagents and the training, this was wildly enthusiastically received. For instance, in Eastern Sarawak, it's sort of a neglected area, and very different from Kuala Lumpur. It's province of or Sarawak state is somewhat ugly stepsister, if you will, and they don't always have the health facilities. They had no place to, in this state, to really even diagnose dengue or influenza. So we helped them get real-time thermocyclers in there and helped them bring it up, and it was very useful to them. In fact, it was the infrastructure for their response outside of the capital of the state to COVID. This became a testing center. So anyway, I just say that this is a nice approach, bringing diagnostics to the developing country, not just for a handful, but a bunch of pathogens that are common, and then supplementing that with pan-species diagnostics that we would often do when they send us the specimens. So setting up these labs got a lot of publicity, a lot of thanks. One of the hospitals we set up was 3 hours downriver in the jungle, and it's there that we found a number of different problems that we would only see in tropical infectious disease textbooks. So a lot of opportunity for spillover events from wild animals. The other thing that we benefited from with respect to One Health approaches is the knowledge of environmental health professionals. I'll just say that, I didn't get a lot of this in med school and didn't get a lot of it afterwards. But boy, have we benefited, from learning how environmental health folks sample for toxins. And sometimes we're able to take those same instruments and look for infectious agents. So that's what we did. We worked closely with the CDC. They have developed this NIOS two-stage biosample you see here in the lower right of the screen that not only can detect nucleic acids, but sometimes it can pick up live viruses if you process it quickly. And it separates them into 3 different particle sizes. And it's small enough, as you see in the upper left here, here's Kristen, one of my postdocs. She led a team riding the subways in Singapore for a whole year with these. The idea was how much virus is being transmitted in the public square in these crowded facilities. So we've benefited greatly. These are another non-invasive tool to get at the problem of aerosol transmission. We've done this in the healthcare settings, in agriculture, even in associated with the Hajj in Saudi Arabia. They have a lot of respiratory epidemics, and then airports, and then in Singapore's subway system. So thanks very much to the collaboration, particularly of the CDC's colleagues. They showed us how to use these, and we're able to learn a heck of a lot. Instead of trying to sample one bird at a time, we can sample hundreds of birds through these aerosol samplers, especially in these dense live bird markets. And if we quickly, freeze the cyclonic samplers, we can get live virus. We demonstrated this not only in Hanoi, as shown here, very high prevalence, 90% positive aerosol samples with live virus. But we also did this again in China in a moderately busy live bird market. So I'll just say that the opportunities to use these, they're very accepted. They're mobile, and they greatly have enhanced our understanding of transmission, not just for these respiratory viruses, but also for emergent events. We brought these into the hospital at Duke, and both in Singapore, Duke US Medical School in Singapore, and also at Duke University, and we're able to detect at least the nucleic acids, but found that getting live virus is really a challenge. So they're useful. Another thing we've done is use them as early warning systems in partnership with agriculture. Ben Anderson now is an assistant professor in Duke Kunshan University in China. He did some pioneering work in North Carolina farms and demonstrated that he could pick up an incursion of virus 1 week before the veterinarians were called in. So molecular signature said, "You got a problem?" He called them and says, "Yeah, we do. We just called the vet." So a very sensitive approach. And another postdoc, Emily Bailey here on the right, used fecal source indication, and it was successful in looking for targeted viruses with molecular assays. But I think where we're headed is next generation sequencing, metagenomic approaches. If we can do data reduction and data software pipelines in a way that's cost effective. This is the Chan Zuckerberg Biohub, now called something else, CGID, I think it's called now. But basically, they had a vision led by Joe DeRisi of University of California, San Francisco, to use a next generation sequencing approach in the developing country to circumvent all the problems we have with moving specimens, not having permission. Actually give them a sequencer and the training and the supplies to do this on focused projects. Most of this was at the human-animal interface, but we were privileged to look at some of those same fecal slurry in pigs, and Emily Bailey and her colleagues basically use this wonderful software pipeline. It's a graphically rich, quantitative for conserved sequence, a way to approach novel virus detection. And when you see, for instance, these fan-shaped graphics that tells you may have a new strain because it's not aligning well with anything in you know, the um, GenBank, and so you need to drill down further. But in a matter of hours after you process the specimen, you'll get a readout that'll help you. Now, this is a paper that was generated from this teamwork, looking at these specimens, and I think it's very telling. From 9 fecal slurry samples, they constructed, it didn't happen overnight, it took like 3 years, 1,792 viral genomes, of which 30%, 31% were novel, and the discovery of a number of different viruses we'd never seen before. So I'll just say that, again, many of you know this, that there are a lot of viruses yet to be discovered out there. And if we have the tools to look for them, of course, the trick is, you know, what do those viruses, when they're detected, mean? Are they a human threat? Well, we've used this One Health approach to make a number of discoveries. We found evidence that the metapneumoviruses were jumping back and forth between humans and turkeys. Equine influenza was infecting camels. Influenza D was in chickens for the first time. We found a vampire bat adenovirus in a little kitty with pneumonia. Then they had no vampire bats. Not sure what that means. And some human enteroviruses in pigs that shouldn't have been there. A feline adenovirus in humans. And most recently, a canine, I'll talk about in a minute, coronavirus in humans. But what do you do when you find this? You need to have some sort of strategy. Of course, we can't do Koch's postulates because you can't really challenge people, but we have to fall back on Bradford Hill criteria that you know well, or Falco's criteria. And it's usually an incremental process where once you find a pathogen that may be associated epidemiologically with clinical illness, you know, how do you have to develop immunologic approaches to further study its risk factors and spread and that sort of thing. Again, other disciplines getting involved. Well, that's the story I want to tell you next. We had the fortune for many years until recently, when China sort of pulled back on this, they would send us scholars to come hang out in our labs. And this young scholar, Li Shanju, came from a leading university in Beijing and had a lot of molecular diagnostic capability experience. So when the SARS-CoV-2 outbreak began, I said, Li Xing, could you develop a pan-species coronavirus assay? And that's what he did. He did a semi-nested assay, and we ran it against all the coronaviruses we could that we had, and then you know, synthetic constructs of regions of other coronaviruses, and said this thing worked pretty well. Pretty well against our you know, our key viruses. It didn't pick up other viruses, and then we put it to work on some of our archive specimens. And I'll just say, long story short, we got some strange signals on pneumonia patients in that state of Sarawak that we didn't understand. So we were fortunate to send it to coronavirus experts from the veterinary world, Linda Safe, and she passed it on to Anastasia Vlasova. And after, you know, about 15 months of work, Anastasia had a live virus from one of the pneumonia patients, a second pretty strong signal in another pneumonia patient. And this live virus was a canine-like virus we'd never seen before in humans. And so it just goes to show you, if you have the tools and you look, and this was, I think the group we looked at was less than 500. So what's the probability of picking these up in your hospital settings? I don't know, but if you're not looking, you're not going to find them. I think it's remarkable about this. So what are we doing next? Well, we basically partner with immunologists to develop a better understanding of this virus. We you know, are developing serologic assessments, and we've just been funded by American Lung Association to do an epidemiologic study in Sarawak to get a better handle of how prevalent this is. Now, we're not alone. As soon as we published this paper, Anastasia led it. A number of other spillover events were realized. One had been a paper of, published before this time where they saw evidence of in human respiratory patients in Arkansas. This is an FDA immunologic researcher, Dr. Marley Azevedo, who found this, and suddenly we realized that she had perhaps found something very similar, a novel corona. And then there were two other discoveries. John Lednicki at the University of Florida discovered both a Delta coronavirus and a canine-like one. It was 99.6% similar to the one that we found. He found both in Haiti, so more than 1,000 miles away. So that suggests that perhaps our virus had been circulating for a while. We don't know of any great conduit of people moving back and forth between Eastern Malaysia and Haiti. So let me just summarize here, and maybe I've caused you to think a little bit about the One Health approach by saying that we think we can do surveillance, targeted surveillance, data reduction surveillance at a lower cost, and it's more sustainable. And it's if we do this in an incremental fashion, low tech to high tech, we engage multiple disciplines in problem solving. It's very popular to bring the technology to people in the developing world. Instead of just taking their specimens to our lab, they're a center partner, an important partner. It has, as I mentioned, the narrower focus is something that we think is sustainable and doable. So I'll just shut down there and see if you folks have any questions for me. Now, I'm an epidemiologist, so go easy on the immunology questions.
Okay, so we have a couple of questions, both from Satya in the chat, and I'm actually going to ask Satya to go ahead and read out her questions, since we don't have a whole bunch. We can start with her asking you herself. You want to unmute yourself, Satya?
Yes, great presentation. Thank you. And what this clearly shows is there are so many coronaviruses circulating among animals, and the exposure to humans may be more common than what we realize. What are your views about cross immune reactivity among these viruses, and what level of protection they may have or potential to provide immune protection against the exposures?
Yeah, well, I don't think we have a lot of information about cross reactivity just yet. Ralph Barrick is attempting to bring these up, and I think he has panels of sera, and he'll be able to get more at that question. But I would agree with you that, these viruses are challenging humans' immune systems probably in all of our own backyards. And if you live in an area where there's, I think, either intense wildlife exposure, but more importantly, intense big ag farming, you can pick this up. It's unfortunate, though, that there's been resistance. And so we found, I don't want to name any names, but one of the leading veterinary diagnostic labs in the United States, a virologist there wanted to use these techniques on specimens he was getting all the time. But as soon as they heard we were interested on the human side, he says, no, I can't do it. In fact, to do anything like this, not only do I have to have permission from my institute bosses, but I have to have the state veterinarian's approval. So a tremendous threat. We're just seeking knowledge, but they see it as a threat. You find a novel coronavirus associated with our livestock, it's going to hurt our business. We don't want to know. So we've got to find a way to partner with them. We think the way to do it is to say, look, you use these techniques, we can tell you when African swine fever or some other classical swine fever or something is in your populations with some of these pathogen discovery techniques. why not do it? But they're a little bit narrow-minded, I think. We've got to show them that using human side diagnostics can help in their production.
Mitzi, you have a question?
Yes, I do. Greg, that was a great talk. My question is that whenever an infectious agent jumps from one species to another, is it more prevalent in the same like mammals versus from a mammal or from an avian to a mammal, or to a lesser extent between a fish to a mammal?
Yeah, I can only speculate there. There are modelers that, have focused on interspecies transmission, and they would be better to talk. I will say that there is a paucity of data regarding spillovers from sea life to humans. In fact, we've been wondering about that. You have all these fish farms, and I don't know if you're aware, but almost all the shrimp industry in Thailand was wiped out with some microbic threats. So they're enzootic, threats to those animals, but we don't see the spillover that you do. The zoonoses that originate in pigs, in cattle, in poultry are much better recognized. Are they more common? Probably, but I don't think we've well documented the studies of aquatic life and human interface, except for bacteria, maybe.
Thanks.
Jim Samuel, want to go ahead and ask your question?
Dr. Gray, that was a superb talk, and you've been a leader in this field in One Health for a long time. I'm at an institution that has a vet school and a medical school and a public policy institute. And if I understood your background, you also have some play in the Public Policy Institute. And I think that space that we're losing the battle as informed scientists and educators is the battle about public policy. I'm afraid that the argument, it has to be how to increase the awareness of US and diffuse the politics associated with surveillance. So the solutions that you provided are examples that you've had and examples in the future about increased surveillance. And I'm just wondering what the strategy would be that you would change the dynamic that we currently have, because I think that's an essential thing that scientists and educators have to be part of developing.
I wholeheartedly agree with you. We've got to find a way forward. Just think of what this novel virus did to us. Who knows what'll come next? I'm a consultant for a company that has the only adenovirus focused vaccine, live one, and they just got told by the FDA that no way do they want to risk, chasing adenovirus. But what happens if we get hammered with a novel adenovirus? There's nothing that is available for all but 2 of the adenovirus 100 strains. I think I'm very much in favor of the soft stick approach, not using a big stick, but some people have advocated that we need legislation, just like we have legislation in policy that has no acceptance of any avian flu in poultry. That's not true, of course, in much of Asia, but there's testing and all, and culling if we find any. But most of that's driven because it protects the companies that produce the poultry. Some sort of legislation, some people say, is probably the only way forward. We've been trying to partner and say, look, if you take this, medical schools are funded 50 times, I at least, roughly, have 50 times the research funding that veterinary schools have, roughly. So use us to improve, your knowledge and your care for animal health, and use us to protect your businesses. Is there some way we can come at it, together, sign, non-disclosure agreements to protect particular facilities. I've been singing that song though for some time, and I'll just tell you the big producers, they will give you some rhetoric that, yeah, we're concerned, but do nothing. So I don't know what to, maybe if you're involved in policy, you can do better.
So you feel that a problem is the production industry. And if we had a better relationship with the production industry as One Health advocates, we would make a better policy.
If we could protect their interest and allay their fears, yeah, because they want to know what threats are coming in. People are just going bonkers right now, as you probably know, with the threats, African swine fever that's circulating in Asia, and FMD and high path avian flu that's now in Europe. What is that going to do to the U.S. industry? And if they could leverage our resources, I think it'd be attractive, but we would have to protect them somehow, and that may take legislation as well. I wish somebody like your institutes could tackle this, head on. I'm just a researcher. I don't know how to do policy. But what we need to.
I was going to just say that, what occurs to me with this ongoing bioaerosol surveillance, which I guess you envision that just to be an ongoing thing, not just a random sampling, but a continuous system in place. I mean, clearly the challenges for unknown organisms that are discovered, what's the benchmark to act, and what do you do, right? It's obviously extremely useful for organisms that we're already aware of, or things that we've discovered that are related to known threats. But if you discover something novel is in a given population, I guess you have to wait for disease to appear, right?
I don't think we can wait. I think we need smart people to evaluate those data and say, look, we pulled from the air of this dense population group of animals this novel virus. It is 75% different than anything else out there. Then we need to say, is there serologic evidence in the animal workers that it's causing invasive disease? Is it in the air passages of those people? Is it live in the air or just nucleic acid? So there's sort of an incremental investigation that needs to go on. But right now we're doing nothing. I mean, nobody's doing surveillance. Do you know that there are pig farms going up in China with 50 or 60,000 heads of pigs? I mean, can you imagine? It's like you get a novel virus in there. They have good biosecurity. You get a novel virus in there, it is just churning and churning. The scale of these CAFOs is pretty amazing. We'll never go back to small farming. I'm not saying that, but I'm just saying the potential for novel virus generation in the next 50 years, not just in China or the US, but everywhere. The big agriculture is being taken over. It's going to be tremendous. These risks are not going to go away. They're going to continue. And when they don't cause disease in the animals, we're not going to know about it.
Wow.
Anyway, I wish you guys well. You're raising the next generation of researchers. It's a complex world, and thanks so much for having me join you today.
Well, thanks for much. That was a great talk, and so we can give you a virtual round of applause.
Okay. Okay.
Really appreciate you being here.
Thank you. I'm going to